Our next topic is potential energy, and the direction we're going with this is we saw from the very beginning that we're going to need more than one form of energy to be able to really tell the story of the energy in a process and where the energy goes and what forms that it takes. And again, this is a broader category of types of energies. It says there that potential energies are associated with conservative forces. And that word conservative forces, like you ask, like, well, what's the definition of a conservative force? And actually, if you Google that, you might find a conservative force is a force derivable from a potential energy. And of course, that's incredibly circular. It turns out there are some better definitions than that. And we have the next topic is actually going to focus a little bit on conservative forces and what their general properties are. But two examples are gravitational force and the spring force are actually both examples of conservative forces. And generally, the property that potential energy has is that if you put energy into the form of a potential energy, that energy can come back out, transform back out, generally into kinetic energy. Like, in that sense, like if you have an object, like let's say I take an object and I toss it upward, it started with kinetic energy. That kinetic energy becomes gravitational energy, which is an example of a potential energy. And then it converts back into kinetic energy as it falls back down. And contrast that with, like, if I push an object along a surface, I won't expect that object to spontaneously return to me because of the friction force. And in that sense, the friction force is not a conservative force. I don't expect to get the energy back. Potential energies, in that sense, all have the capacity to kind of act like a battery. You can put energy into it and you can take energy out of it. Whereas with friction, it's more problematic. You can put energy in, but good luck getting it back. You're not going to get a slight increase in temperature of a surface to suddenly push a system. It's not that easy. Again, the details get a little bit more intricate and mathematical, and we'll put some of those off, and we're not going to go into full depth on that anyways. Let's look at some of the other key concepts here. One of them says here, the defining the system is important. So with the introduction of potential energies and the fact that they are associated with forces, we're going to have to discuss a little bit more what we mean when we say that we're defining a system. Again, that becomes more intricately tied with the analysis with these kinds of situations. Here is a general formula. It says work is equal to change in kinetic energy plus a change in potential energy. A formula that I actually don't think I ever have in any of these slides, but that is one that I've sometimes made the claim I can do all energy-based problems starting from this formula. That may be too big a claim. Maybe I should have said almost all. Is the idea that work is equal to a change in energy in a system. This specific instance of that formula is for a situation where work is changing the mechanical energy of a system. And as we saw, mechanical energy broadly fits into two categories, kinetic or potential. And it's really potential energy that has a great deal of varieties of it. So really, this is kind of like, this really follows from here. But I often like this one because it's a very good starting point just conceptually for problems. So you might see me using that for some problems as we go through. These are the two specific formulas we're going to associate with two potential energy forms. We've already seen gravitational potential energy in the introduction. It's equal to weight times height. But in terms of mass, that is mgh. And height always needs to be defined relative to some ground level spot that you're regarding as representing zero gravitational energy or gravitational potential energy. And then there's the spring potential energy. This formula might be familiar because we looked a little bit at work done by a variable force. So if you compress a spring where you're kind of acting against Hooke's law, F is equal to kx, then the amount of work it took to do that was equal to 1/2 kx squared. This formula looks the same, but it has a slightly different perspective because if I compress a spring, what I think I'm doing is I'm doing work to it. I'm putting energy into that spring, and that spring is storing it. And that's the characteristic of all potential energies, that they represent a way of storing energy. And then if I let go, maybe the spring uncompresses and launches some object. Maybe it's a pinball launcher or something like that, right? And since it's a form of potential energy, it has the capacity to do that. So this formula looks the same as that work formula, but has a different meaning. This is the amount of energy stored in a spring potential energy as a function of how much the spring is either compressed or stretched. So X still has that meaning. K is still the spring constant here. These two are basically two additional tools now. We still have kinetic energy. Both of these can then feed into this to solve problems.